Hello everyone. In this lecture, we are going to discuss about the topological spaces. First, we will define the topology. What are the conditions? What are the criteria for any, the collection to be the topology? So, as you clearly seen here that let X be a set. Suppose X be any set. A topology tau on X is a collection of the subsets of the X. Okay, so actually we are X is the collection of the subset from this set X. We are actually choosing the subsets of that set, so that such that phi and X are in tau. Actually the tau is basically the collection of the subsets of X. Okay, so for this phi and X should be in the tau and the sub collection that we have taken, and we will illustrate this from the example also in the below. So another is that the intersection of finitely many members of tau is in tau. Okay, we can we are choosing finitely some members, and if we take the intersection of those sets, that those intersections should also lie in the tau. And another criteria is that the union of any members of tau is in tau. We are taking the union of the sets, and and the such union will also fall on that topology. Okay, tau. So the set X together with the topology tau is called the topological space, and it is written as simply x comma tau, or sometimes we generally write, for simplicity we are just saying that X is the topological space. Okay, so here actually X means the set, and the tau is the sub collection that we make from the X, that is called the topology. So now for any set there can be there can be many the topology. Okay, so let us look it through some examples. Let us look at to the example like this. Here we have X is equal to ABC represents any set. Okay, let us take a collection where phi AB and ABC means X itself actually. So if we look at to the criteria for any subcollection to become the topology, the phi and X should be there. Yes, here in this collection also we have the phi, and the X means this ABC means whole set. That's fulfilled. Another thing is that if we do the intersection of any sets. Okay, if we do the intersection of A and AB, we get A, then A is there. If we do the intersection of AB and ABC, we will get AB is also there. Okay, so in this way, the if we intersect any sets, the intersection will also lie in the same topology. Okay, if we look at to the union, okay, let's say we are doing the union of A and AB, and that will be AB is there. And again if we do the union of the A and ABC, we will get ABC is there. If we do the union of AB and ABC, then again the union is ABC, that is also there. So it implies that all the three criterias satisfied for this sub collection. This collection represents topology because both phi and X are there. Yes, phi and X are there. Also the arbitrary union of the members of the members of tau lies in tau, and finite intersection also lies in tau. So tau represents the topology. Let's do go to the another point. In this example we have the set X is equal to ABC, and the topology is like this: phi and A, B, ABC, AB and C. The first criteria is that the phi and X is there. X means the whole set is there. First criteria is fulfilled. Now let us take the unions. If we do the union of A and B, we get AB. AB is here. If we do the union of ABC, we will get ABC. ABC is there. if we do the union of ABC and AB, C there, okay. So if we do the union of AB and C, then again ABC. If we do the union of the A and the C, if we do the union of A and C, we will get AC, but AC is not there in this topology. So in this sub collection we can say. So that's why we have to say that tau is, if any if that criteria is not fulfilled for any one, if for any one, like say set, we call that topology, we should not call that sub collection as the topology. Okay, so I hope you understood that. And now we do not need to go ahead, we do not need to check the finite intersection will lie in tau or not, because the condition is not hold for the union, so it implies that it cannot be the topology. Okay, so again let us go ahead. The formal definition, if we write the definition is in little bit symbolic form. The collection tau of the subset of X is topology if phi and X belong to the tau, and if G alpha belongs to tau for alpha belongs to A, then union of the this G alpha is actually the sets, the subsets of basically the f of that set X, which are lying on the tau. So if we do the arbitrary union, arbitrary union means any, we can choose any number of the sets for the unions. Okay, so the arbitrary union will also lie in the topology, and similarly this one, the finite intersection, because we are taking I is equal to 1 to n, finite intersection should also lie in the topology. So we have already discussed about that. So let us go to the another point, and that's the open sets. What are the open sets does mean? The open sets are also called as the member of the topology tau. So let X be a set. A topology tau on X is the collection of the subsets of the X. Okay, a topology tau on X is the collection of the subset of X. We know that. Then each member of the tau is called the open sets. Okay, this is very clear. If we have the topology, the each sets of that topology are called the open sets. Okay, let us take one example. For example, X is a set and the tau is the topology is defined like this. Here all the sets like phi, X, A, B and ABC. These are the sets lies in the topology. So this A is also like, so here A and BC, phi and X, all these are the the open sets. Okay, so let us again move ahead to little bit. Okay, so let us now let us discuss some the types of the topology. So the first one is the trivial or indiscrete topology. Take any set X and let phi and X, where the elements are, one is the two elements, one is the phi and another is the whole set X. The topology, this fulfills all the criteria actually. If we take the union, if we take the intersection, and as there the phi and X are there, so this also holds the property of the topology. So that's why this is the trivial topology. The trivial topology means a topology which consists of the two members phi and X. Okay, so let us move ahead. Another one is the discrete topology. So discrete topology means let X be an n set and phi be a set of all the subsets of X. Actually the phi, we know that phi is actually the sub collection taken from the subset of the X. So actually we will take all the subsets, we will choose all the subsets of X and make a set. That's also called, we can say, the power set. So such topology is called the discrete topology. Okay, so in discrete topology it consists all the members, all the possible subsets of X, or we can say the as power set, the usual topology of R. Okay, so let X be the R, and tau, and tau be the collection of all the sets, or the open intervals, the real number set. Then tau a comma b, and where this ab is the open interval, like 1 comma 2, 2 comma 3, like that. So where AB belongs to the R, and there is phi also, phi should have to be there. Then tau is the topology for X, and it's called the usual topology. Basically, usual topology means the topology which is related to the real number set R. Okay. So okay. So again, this topology, this usual topology is also called as the standard topology or Euclidean topology. Now let us discuss little bit about the closed sets. The closed sets is okay. The closed set is basically the can be found by making the complement of the members of the the topology. For example, we have some topology like this: phi a, ab, and abc. Okay, if we take the complements, if we take the complement of those members, we get what? The complement of phi means X, the complement of okay, so here in this case the whole set is X is equal to abc. Okay, so the complement of A will be bc, complement of ab will be c, and complement of abc will be phi. So that's why these X, bc, c, and phi are the closed sets. Simple, in the simple term, like the complement of the complement of the members of the topology forms the closed sets. That's all. Okay, so thank you very much. In the next video I will bring some another the topics related to the topology. So thank you very much.